This video is brought to you by Hackeramo Chalk. Use code TPSA 10% off to get a discount.
Welcome back to the next lecture in the TPSA IBM Qiskit Fallfest lecture series. In the previous lecture, we looked at some of the foundational aspects of quantum computing, from the fundamental physics that underpins their behavior, and also some of the applications and use cases they can be used for, as well as their architectures and the types of qubits and the potential for the future. In this next lecture, I'll be taking you through how to use quantum computers either as a student or as a researcher using the IBM software Qiskit as one such way of doing that. So, first of all, what does using a quantum computer look like? As mentioned in the previous lecture, they have to be cooled down to extremely low temperatures, ones that would make them impractical for use, such as being a quantum laptop or a quantum desktop. So their operation is better served more as a cloud computing service. So as we can see here, we have a user and a cloud server as your self-contained what you have access to, and your quantum programming language, which we will refer to as Qiskit in the next stages of this lecture. And once you code a particular problem, you can then access through the cloud service your quantum computer itself, send off the code you wish to run, and then perform that on the quantum processor by converting the code through a series of stages into the pulse sequences, which are the physical way of performing the quantum gates, which you will code into your quantum circuits. So what is Qiskit? Qiskit is a software development kit developed by IBM that works with quantum computers and allows you to build circuits, simulate them, calculate the expectation values of operators, and do a variety of other things as well. So it is built up of a few different components, but when using the term Qiskit, that will generally be used to refer to the whole collection rather than any specific part of the software. For example, there is Qiskit Runtime, which is used as part of the cloud service and helps execute workloads on the actual quantum computers and manage data transfers in that sense. The Qiskit ecosystem is then the collection of software, tools, and projects that are more influential in the wider Qiskit community for people to work on than, say, a specific part of the code itself. So currently we are on Qiskit 2.0, or I think 2.2 was released recently. And Qiskit on the whole is a Python-based programming language, but with Qiskit 2.0, it has introduced C capabilities as well, just for flexibility in terms of the type of programming language you want to use and execute Qiskit on, but still Python will be your most commonly used programming language. So it allows for faster circuit execution and transpilation, terms which will be explained a little bit later on, and then has features still referred to from older Qiskit versions, such as dynamic circuits that allow you to collect information while mid-execution of a quantum circuit, for instance. So to install Qiskit, there's a few ways you can do it. In coding environments like Anaconda, if you want to run Python through any of the means available there, you can install Qiskit in the Anaconda environment, installing different components. So Qiskit visualization here will be your broader Qiskit features. Then you will separately install IBM Qiskit Runtime and other features such as the transpiler service, for instance, if you want to look into that. Of course, you can also use Qiskit without installing any of them locally on your device through Google Cloud Notebooks or QBraid as another option. And in future tutorial videos, Google Cloud will be used just to highlight how this works. Then if you want to access the hardware itself, so go beyond running code locally on simulators, you would need to then register for an IBM account and set up a token for your local computer to then access the Qiskit Runtime Cloud service and connect with these actual quantum computers, which some of them are freely available to access for anyone who does have an IBM quantum account. So Qiskit. Qiskit is this collection of software tools referred to previously, and this simplified workflow here kind of splits up how exactly the whole system works. So we have this dashed dividing line splitting off Qiskit for the coding software workload manager that would be used by researchers. And then in the lower section, we have the quantum computer itself, managed by Qiskit Runtime, connecting to the quantum processing unit, which in the case of IBM hardware is a superconducting chip. We also have high-performance classical hardware to use as well, because with quantum computers they are prone to errors as noted previously. So if there is some component of the workload such as error mitigation, or you are executing a hybrid quantum classical algorithm, you will also access classical devices as well, rather than running everything solely on the quantum device. So you will have Qiskit for the manual input of the problem, and then this lower component of the diagram will be your hardware section. Of course, we can make this a bit more complicated and specific by not just referring to Qiskit on the whole as Qiskit, but breaking it down into component features that it possesses. So on this top level, we have the abstraction services. So what this is mainly the Qiskit functions catalog, a new Qiskit feature which is still only for premium users, not fully available just yet, but it contains pre-built code for specific features for error mitigation, state preparation, specific functions essentially, which are useful for Qiskit users to not have to spend time coding themselves, but can then use from this catalog and dedicate their time to algorithm discovery, developing the problem itself, rather than coding specifically useful features that Qiskit have decided to be prominent in their code. Next, we have the development tools, so the Qiskit SDK, the broader software development kit for Qiskit that most people will access directly by coding their circuits, sending off jobs to the quantum computers themselves through Qiskit runtime. And then we have Qiskit add-ons, which is extra features that use specific methods to, again, similar to Qiskit functions, help speed up the process with inbuilt functions and features for mapping quantum circuits to quantum computers, improving state preparation, and speeding up the general process. Along with this, we have the Qiskit transpiler service. So within the Qiskit SDK, you can already transpile your quantum circuit to be suitable for the specific quantum hardware you want to access. But the transpiler service just adds an extra layer of complexity to these features by giving it a bit more power and a bit more, I suppose, specific methods to use to really push the optimization of your quantum circuit for the hardware you want to use. Next, in this heterogeneous orchestration layer, you have Qiskit serverless and the Qiskit HPC integration. So this is separate directly from the code development aspect of Qiskit, and is more about managing the workload and the data transfer while you are running your jobs and simulating your quantum problem between your quantum computer and some classical component if required as well. And across all of these services, you have the newly released Qiskit Code Assistant, which is just, I suppose, code prompts that are now becoming more prominent in all different coding environments, with this one specifically made for Qiskit. Then, of course, we have the bottom layer as before with the compute section, so the actual running of the simulations on the quantum computer managed by Qiskit runtime, and also any classical high-performance computing component if required as well. So, Qiskit SDK is developed by IBM, but of course can execute things on quantum computers, and in this case is not restricted purely to the IBM superconducting devices. So we would refer then to Qiskit as a hardware agnostic software, in that it can be run on the platforms of different companies and even different qubit architectures. One of them listed here would be IonQ, for example, which develops quantum devices based on trapped ion qubits, which are different from the superconducting qubits used by IBM. So that shows a bit of utilizability in Qiskit, in that you are not restricted to the devices you want to use, and you can test your problem on different sets of hardware and see do you get any benefits or advantages in your mappings to each of them and your runnings as well. And Qiskit goes beyond just IBM capabilities in its usage as well. So in the Unitary Foundation survey of 2024, it was shown that Qiskit has contributions external to IBM as a whole company, by 74% of the contributions being people outside of IBM, which goes to show the power of Qiskit being an open source software that people can kind of play around with and develop and try to make contributions to without having that direct connection to IBM. There's also 5,185 Qiskit dependent projects that are, I suppose, research level or general interest level that allow people to just take Qiskit and tackle a specific problem that interests them. So just to show, elaborating on these survey results, we have a few different components of Qiskit here on this bar chart, but again, Qiskit broadly would refer to all of these components together rather than having to split them up. So Qiskit would be used by, let's say, 74% of people, and the next highest software usage would be PennyLane, and we keep going down the list until then. So Qiskit, being the focus of this lecture series, has the benefit of being the most commonly adopted software to be used. So you have, I suppose, access to more people that use it, more advice, more inputs, more collaborations because of that. So we see that with the speed of Qiskit, you have 5 minutes overall time to complete some problem. You have other softwares that would give different results or different runtimes for the specific problem. Then we have extensibility. So again, going back to that project access for how many people use Qiskit for their own problems, own research. We see 4,388 dependent projects, with the next best being 1,150 taken up by people using PennyLane. And then we see 445 dependent projects with maintainers and some form of support, and the next best being Circ by Google, which is actually not a Python-based programming language, but one which is C, I believe. Now, of course, choosing a quantum programming language, you can use a favorite one, multiple, or one that suits how you prefer to code, whether it is Python-based or C-based, or having any specific problem, specific features that you would like to use as well. So it is encouraged to also explore other options and really develop your understanding of quantum computing through being able to transfer it between different softwares and not just relying on the software to handle aspects of your knowledge that you want to develop theoretically as well. Moving beyond general Qiskit, we'll focus specifically now on Qiskit runtime. So this little diagram here shows us where runtime comes into the problem workflow for running problems on a quantum computer. So we would have our laptop here where we develop the problem. It goes off to the cloud and goes over to the IBM systems. It is then managed by Qiskit runtime, where that will handle the data of the problem on the quantum device, but also on the classical device. So you'll run the problem or your program on the IBM quantum platform, and you can use both quantum and classical resources to handle that. So rather than you simulate a quantum part of your problem on the quantum chip, send the data back to your laptop to optimize parameters in a VQE algorithm, for instance, and then send the next iteration of the problem back off to the quantum chip, involving this constant communication and data transfer between your laptop and quantum chip. Qiskit runtime will help make that more self-contained and more, I suppose, in-house with specific IBM classical resources rather than your laptop to quantum chip constant communication. So this would be useful for a variety of large-scale problems that, again, VQE is one example. Any hybrid classical quantum algorithm will definitely involve that, and any even specific quantum algorithm that you want to perform classical error mitigation post-processing of results on as well. So you have several execution modes with Qiskit runtime, such as job, which is the simplest to send a job off to a quantum computer, session for sending, I suppose, multiple jobs back and forth, and then batch for single multiple job submission as well. So this can all be explored in code for more detail, more practice to make it much clearer. And as highlighted before, if you want to install it locally or in a Google Cloud notebook, you can install it through pip using that below code. So what runtime does to, I suppose, execute the problem is it has two primitives. These primitives highlight how to do two different types of computations with quantum circuits. There is the estimator primitive and the sampler primitive, which both have to be imported in Python with their version 2 forms, since version 1 are depreciated. So the sampler will run your quantum circuit, and what it does is it returns the counts for each measurement outcome. So that allows you to extract raw measurement data out of your circuit and see how many times each of your classical bits from the circuit were measured to be 0 or 1. Whereas the estimator takes a extra input, being a quantum observable, such as a Pauli string, that you want to get the expectation value of after running your circuit, and it will instead return expectation value data for that observable. Now, even though you can run a variety of quantum programs on a quantum computer, a lot of them will still follow the same type of workflow, which is being by IBM named Qiskit patterns, and it's just an anatomy breakdown of how you tackle general quantum problems. So for instance, you would have step 1 of mapping your problem instance to quantum circuits and operators. So you take any arbitrary problem in quantum or outside of quantum, and you break it down theoretically into a quantum circuit and particular operators you might want to find the expectation value of. And in Qiskit, you create said circuit and give it the operator. Next, you then select a quantum device you want to simulate the problem on, and you optimize your circuit for target hardware execution. So this just basically means that you will have your collection of quantum gates in your circuit, but the quantum computer might not necessarily be able to perform all of those operations directly. It will have its own set of basis gates, which it will have to use to compose any other operation on the quantum circuit that you want to perform. For instance, you could give your circuit a Hadamard gate, whereas your quantum hardware might not have direct access to a Hadamard gate, but will have access to a few different rotation gates and have to use those to approximate to an arbitrarily high accuracy the Hadamard gate. And of course, you would have to map, say, your 20 qubit circuit onto the 127 qubit, for example, processor as well, trying to optimize the connectivity of these qubits. And these are just a few things that you would want to consider when transferring from your theoretical instance of the quantum circuit to the real execution on the quantum hardware. And once that is done, and you've done it to a satisfactory and optimal level, you will execute via Qiskit runtime, either by accessing simulators that will run locally on your classical device, but will emulate some quantum hardware that you say want to do a simple test on before queuing up and trying to simulate on it. Or if you're prepared for that stage, you can simulate it on the quantum hardware, and as I mentioned before with the sampler, you will return bit strings from your circuit, or for the estimator, you will return expectation values of the input observable or observables if you want to check the results on a few of them. Then step 4, once you've achieved this, you can post-process your results to combat any errors that may have crept into your calculations in the process of running them, because even if you're running it classically on your device, you can input noise models which will again emulate better that realistic quantum computing execution that we currently are capable of. And within the Qiskit SDK, there's a few features in it that will help you perform each of these steps. For example, in creating the quantum circuit, you of course have the quantum circuit library, where you create your quantum circuit object, put the gates on it, and can measure at the end. For optimizing the circuit, you would then run it through the transpiler to varying degrees of complexity, depending on how optimal you want to make your circuit. And when it is done, you will return this ISA circuit, which stands for Instruction Set Architecture. So you've converted your circuit from having arbitrary gates, the instructions you wish to perform on the qubit quantum states, and you are setting it up in the architecture with the instructions that are available on the selected quantum device you want to test your simulation on. Then of course you go to the primitives from Qiskit runtime, giving it the ISA circuit and potential observable, and it will return to you your measurement counts or expectation values. And after this, you can input your measurement results to some error mitigation processes and then return better counts from your results or improved expectation values as well. Now, returning to this Qiskit add-on feature mentioned earlier, these of course add extra layers of capabilities to each of these possibilities within the Qiskit SDK. So for example, we have these multi-product formulas in the Qiskit circuit library. So these multi-product formulas are not inherently quantum, they are actually a set of tensor network methods that are quantum-inspired classical methods, but can work to efficiently store your quantum state classically, and again ease that quantum workflow and dedicate it solely to the part of your problem where you gain a quantum benefit and therefore have to use less quantum resources, meaning less noise in your results as well. We have, for the transpilation, circuit cutting, for instance, that can break up your circuit into a few pieces and transpile them in more complex ways than feeding it through, say, a preset generalized transpiler that might be your first method of attack on transpiling your circuit. For your quantum information section, your error mitigation, there is the sample-based quantum diagonalization method, which is a hybrid quantum classical method for diagonalizing a system, but uses some error mitigation techniques built into it as well to combat counts in your bit strings that come out, and that will be something we explore in a future Qiskit tutorial video. So what these, I suppose, add-ons can achieve for Qiskit is, rather than having to work with the most basic tools that you have access to and add extra layers of complexity in your own code, which will take more research time out of your work, these are very commonly employed methods that have been found to be quite successful and therefore have been accepted into the Qiskit add-on package, and will give people a way of accelerating their research through using these already built-in techniques that, of course, should be understood for why they are applied to your problem, but will save you time on why in fact you have to code them and use their built-in methods already. And that can accelerate your work by the statistic given here of up to 5 times. So there's a few papers shown here on the bottom just to highlight exactly the evidence of that. So again, Qiskit Functions is a similar feature to Qiskit add-ons aimed at accelerating the development of algorithms and problem discovery through built-in features into Qiskit that you will save time working on developing independently. So this is not an IBM specific initiative, but has accepted submissions from the wider quantum computing ecosystem to develop this catalog of utility scale specific services, so services that will work at the largest scale of currently available quantum devices that will allow for circuit functions, for instance, to be discovered with new algorithms and for new applications that we don't need to necessarily manage transpilation, error suppression, or error mitigation on directly ourselves, but it will be there for us to use already. And then for applications, for example, data scientists and enterprise developers can integrate quantum into industry workflows, which helps, given that people that can benefit from quantum are not necessarily only people that will have knowledge of quantum. So it is useful to develop means of working on problems outside of quantum in a way such that they are accessible to subject matter experts in those fields. And then we have the wider Qiskit ecosystem, where the likes of you and me would come into this, where it's not dedicated Qiskit employees or Qiskit workers, but people that can still learn from, example, the Qiskit learning documentation, the IBM quantum learning platform, and get stuck into open access Qiskit projects and develop parts of the code ourselves. So there's open source projects that will fall under the Qiskit interface, but we'll look at specific functions for, say, transpilation or applications and so on. So this is why Qiskit from the beginning really was designed to be extensible in a way that lots of developers and interested parties, students, anyone, can get involved, work through code, and take that code on themselves and develop it in such a way that they, in fact, could make contributions themselves to the code. So for example, Qiskit Air is one that is commonly used in Qiskit itself. It pops up quite a bit where you use quantum computing simulators that use realistic noise models. So this is developed in-house by IBM and is for running quantum simulations locally, but that emulate the quantum computing or quantum hardware version of the simulation. Another one is the QBraid software development kit. So this is again platform agnostic quantum runtime framework for the lifecycle management of quantum jobs, and notably is developed outside of IBM. And we have this M3 project. So this is to implement matrix-free measurement mitigation techniques, so tackling a very specific problem for error suppression and how to handle measurement errors. Is again an IBM quantum project. But if you are curious and want to take a look through the list of projects yourself, you can see many projects across many different aspects of quantum and Qiskit that might grab your interest. And the link is here and can be found across the Qiskit documentation as well. So that wraps up this, I suppose, shorter introduction to what is Qiskit, how it is structured, and what the workflow of your quantum computing problem might look like. And the remaining lectures in this lecture series will now focus on getting to grips with Qiskit code itself, using it, and tackling problems of varying complexity.